The world of people dealing with data can be divided into two groups. Those who actively back up the data and those who will soon realize the importance of doing so. The loss of data and its consequences will inevitably happen sooner or later. It's important though to know that comprehending how data loss happens doesn't make us immune to making mistakes, and protecting from these situations is always a hassle. If you aim to create a comprehensive backup system with workstation capabilities, meaning that you don't store any critical data on your personal computer, the out-of-the-box solution can quickly become prohibitively expensive, overly complex, or even entirely impractical. Unfortunately, there are no real effortless options here. You have to consider your budget, technical inclination and future plans for the system's usage. As someone immersed in the tech world while handling photos and videos, my path is clear. I will build a NAS solution myself. This DIY approach will not only ensure robust backup practices but also serve as a storage powerhouse. I will delve into some technical jargon and intricacies, so be prepared for technological wibbly-wobbly timey-wimey stuff.
Good luck.
Building your own NAS is not a one-size-fits-all solution, and it is good for people who really want or enjoy building such a system. In my backup strategy, I'm going to implement the 3-2-1 rule. This rule emphasizes having at least 3 copies of your data stored on at least 2 different types of media, with one of these copies located in an off-site location. The first copy, often referred to as a working copy, is the data we actively use. For me, this primarily includes raw photos and video recordings. This means I can easily attain the level of responsiveness I need from any RAID configuration on standard SSDs. The second copy is typically placed in hot storage. Hot means that the data is easily accessible and stored in a generally explicit and usable format. However, you won't be actively working with this data, so the media performance can be much lower. Because of that, I will be using an HDD RAID configuration. The third copy, which is stored offsite, is typically maintained in what's known as cold storage. Cold storage is designed for high data compression, can have lower read performance and is reserved for rare but potentially catastrophic data loss scenarios. For this particular copy, we prefer additive backup solutions that only store changes to the data. NAS, which stands for Network Attached Storage, essentially consists of computer with multiple hard drives and with software allowing for access to remote storage via a network. First, let's talk about the case. You can find rack chassis and disk shelves at affordable prices on platforms like eBay. However, these are typically built for server rooms and use high-pressure fans. While they are efficient, they will make your vacuum cleaner sound like a bird's play. For a home setup, it's much more practical to use cooling solutions designed for quiet operation within residential environments. When it comes to choosing a suitable personal computer case, the options are somewhat limited. That's why I opted for the Fractal Define 7XL. It's one of the few PC cases that can house more than 16 full-size hard drives, with room for an additional dozen 2.5-inch SSDs. Beyond its capacity, it's a high-quality chassis that's easy to work with. For the server platform, I've chosen a slightly older server-class hardware. Consumer-grade PC components lack the necessary PCI Express lanes and connectivity options to make them suitable for this type of build. I purchased a used Supermicro board with 3x16 and 3x8 PCI Express slots, providing more than enough expansion options for my needs. As for the CPU, I've selected a used EPYC 7551P. This CPU boasts 32 cores and 64 threads. While it may not be the fastest in terms of a single core performance, roughly half the speed of the Intel Core i5-12600K, we won't be playing computer games on this machine. Do we really need 32 cores? Not really. A 16-core CPU would do the job, but the model I chose was a workhorse in the industry not too long ago, so there's a surplus of these parts in the second-hand market. I bought it for just $110, inclusive of high European taxes. Moreover, it's not all about raw CPU power. EPYC processors offer 128 PCI Express lanes, compared to about 20 in consumer-grade builds. This is crucial. And the memory management capabilities are also significant. We will require all the memory bandwidth we've got, as the software for the disk arrays we will be using will make extensive use of memory capacity to cache our working copy data. Speaking of memory, I purchased 4 sticks of used ECC DDR4 RAM, resulting in 128 GB of RAM, with the option to easily expand it to 256 by adding another 4 sticks if necessary. For the actual data, I've prepared 8 6TB hard drives and 12 1TB SATA SSDs. The SATA SSDs will be enclosed in such cases. I've got 2 of these. Interestingly, I didn't opt for hardcore server-grade drives as it's often cost prohibitive. The SSDs I've chosen are new yet reasonably priced good RAM drives, while the hard drives are refurbished NAS-grade Seagate drives with a 1-year warranty. Since even server-class motherboards don't typically provide a lot of SATA connectivity out of the box, we'll use old cheap LSI SAS HBA cards to connect all the drives. These cards may not be very fast, but they are sufficient for handling SATA SSD drive arrays. The entire system won't have a discrete GPU, even though there's an option to add a few of them. EPYC CPUs don't have integrated GPUs, but server-class motherboards typically include a very basic GPU for video output, primarily used during system installation and maintenance. So there you have it. A quite powerful machine with ample storage and a slick case. It's quite enough to be put in the same room as my working station. I will connect it to my private LAN network with 10 gigabit Ethernet connection, although I will try to simulate most of the tests with 2.5 gigabit connection, as it seems to be the current home standard. I've already assembled the hardware and installed a TrueNAS Scale, a well-known free and open source operating system for NAS storage. On the main board we have a set of widgets that provide information on CPU and RAM usage, also network statistics and latest storage pool stats. TrueNAS uses the ZFS file system to construct its redundant arrays. What's most important for us is that ZFS is a battle-proven file system with advanced journaling capabilities that enable snapshot creation of your share state. Set of disks is referred to as a VDEV. A ZFS pool can consist of multiple VDEVs. Adding more VDEVs to the pool can improve read and write performance, but it often means using more disks for parity, which decreases the total storage capacity. Keep in mind that stacking VDEVs doesn't make your data safer, because any failed VDEV will corrupt the entire pool. Now let's create the working storage using the 12 SSDs at our disposal. A sensible compromise is to opt for 2 VDEVs with 6 disk 082 configuration. This configuration allocates a total of 4 disks for parity data. As a starting point, let's create a single disk striped pool as a benchmark reference, which we will simply call SSD. We'll leave all the default parameters in place. After creating this pool, we'll access the terminal of our NAS and deactivate the caching solution called ARC. ARC caches file operations in memory, and for proper benchmarking of the storage, it's essential to deactivate it. However, we will leave metadata caching enabled, as ZFS is designed with at least metadata caching in mind. For benchmarking, we'll use a tool called FIO. While it's a synthetic benchmark, it provides a rough indication of bottlenecks and overall performance. Our primary use for this storage will be read operation for large files. So we will use random read operations of quite big data blocks, which are very common during video and photo editing. We'll access the shares using Samba, which is single-threaded, so we will measure the performance with only one process and use more only to check the performance surplus for other optional loads on the system. Let's go to the testing and benchmarks for a single VDEV with a single SSD. So the results we've got are quite satisfactory. This particular disk in the simple NTFS configuration on Windows should get roughly 480 MB sequential and 360 MB random read for 2 MB blocks. With ZFS we can observe 427 MB per second in sequential read and 326 MB per second in random operation. Adding additional threads does not change much, which means that the bottleneck is in fact the disk with ZFS file system. Now let's do the same, but this time with a single 082 VDEV consisting of 6 disks. We call it SSD 6 and we'll leave the default options intact. But in this case we want to tweak a bit the record size. Record size is a parameter in the ZFS that determines the smallest data package saved in the file system. The default is 128 kilobytes. When reading just 4 kilobytes of data, the entire 128 kilobytes block must be read, impacting small read and write operations, for instance in the database deployments. However, if we are reading big chunks of data, as with our raw material, bigger record sizes can result in a lower number of I/O operations, potentially improving read performance. The ZFS pool can be arranged with datasets. Each dataset can have its own record size, so you can have custom parameters for your storage and virtual machines disks independently. We won't delve too deep into the tuning side of things, but let's check the same benchmarks for datasets with 128 kilobytes and 512 kilobytes records. The results for our 082 with a single VDEV show more than 1800 megabytes per second sequential read. Random reads are around 5 to 600 megabytes per second with 512 kilobytes record size, giving roughly a 10% uplift for the bigger record size. We are already in the territory of maxed out 10 gigabit connection. Now let's build our main working copy storage consisting of two 082 VDEVs. We will call it SSD pool and we will use it for our working copy and virtual machines. We will leave all the parameters on default and create a dataset called fast data with proper record size. Now we do the same benchmarks. With the configuration of two VDEVs we've achieved 3200 megabytes per second in sequential read speeds, which is approximately twice the performance of a single VDEV. However, in random reads we've seen only a small gain in performance for single-threaded case. The results are quite good, but we are still not using ARC cache. Let's turn the cache on for our fast data pool and perform the same benchmarks. Quickly we can see that we've got a beast of a server that can serve gigabytes of data in all reading configurations, and such performance will be maintained as long as our project will fit in the memory of our NAS. Now we are sure that our NAS is capable, so let's do a practical test. First we create a single user in the TrueNAS system, and this user will be used to access the Samba share from our local network. I've kept all the options at default settings, but there are various things you can customize here, like creating a home directory, enabling SSH connections and more. After that we go into shares bookmark and add a new share. We choose our fast data dataset as our main path and click save. If the Samba service is not turned on, the system will ask us to set it up for us. We enable the service and the shares should be visible on the list. We must add our new user to the access list using the Edit Share ACL option. We add a single entry for our user with full permissions. Upon checking the file system ACLs, our user access should be visible in the list. Alternatively, you can add or modify user and group access through that menu for any child dataset. In our case, we have everything we need to start using our network share. So we go into Windows Explorer in our working station and map a network disk. We put in the shares location consisting of our server address and the shares name, and that's it. The system will ask for the credentials, where you should write the username and the password. In my case, I've done it beforehand and Windows saved my credentials, so it is not asking for the password for this particular share. Now the share is ready to use, and I will start by copying some data. I do not recommend using the system's copy and paste functionality, as it may not always be secure. On Windows, I often use open source Dual Commander that has the verify option that will read written files and check if they have in fact the same content. Keep in mind that this verification step takes extra time, since the source file is read twice. While copy operation is in progress, we can observe how the ERC cache is being populated and how the network card traffic switches from receive to send, with alternating copy and verify steps. Our working station has a 2.5 gigabit connection, and it is fully utilized throughout the whole process. Let's find out if we can use it for video editing though. We put the B-roll 4K material onto the timeline, and we can clearly see that the scrub through the timeline is snappy and without delay. It almost feels as if the data is stored on a local high-speed drive, so let's make it more demanding. I've put 4 different clips on a single 4K timeline and set it to 4 times the playback speed. There are no skipped frames, and scrubbing is as responsive as before. We can see that we are using around 1 gigabit of network connection during playback, so we still have plenty of throughput in reserve. With a 10 gigabit connection there shouldn't be any issues with 8K RAW video editing as well, and probably you would first hit the bottlenecks of the workstation alone. With our working copy storage in place, it's time to ensure its protection. We need a second copy of the data residing on a different medium. That's why we need a new HDD pool. We've got 8 disks, so we built one VDEV with a 082. It gives us slightly over 40 terabytes of free space. Now let's conduct the same benchmarks as before, of course without ARC cache enabled. We achieve a little over 1 GB per second in sequential reads and approximately 100 megabytes in random reads. As we will transfer a lot of data to this pool, I tested as well sequential writes that gave us little above 1 GB per second mark. So now let's use the HDD pool. I created a new dataset called Working Backup, where I want to have a backup of my working copy residing in the SSD pool. In this case, you can probably see that I've already configured a bit more for my needs, but the most important is that I use 2 shares as my working copy. One, called RAWs, is exclusively for photos, and the second, called Fast Data, serves as a place mainly for machine learning and video projects. Now it's time for the snapshots tasks, which allows you to effectively maintain the history of your data. Having the snapshots ready, you can use ZFS send and receive operation for secure iterative transfers of snapshots, meaning you can send only the differences between snapshots as long as both the source and the destination are ZFS file systems. Snapshots are inherently integrated into the ZFS data structure, making them almost instant operations. I will be setting up 2 tasks for my fast data and RAWs folders on my SSD, each with a 4-week retention policy, ensuring a month's worth of historical data for my working copy. Snapshots will be generated every hour, but you can easily adjust the frequency, even setting it once every 5 minutes if you will. Now we create nested datasets in the working backup for my 2 data replicas, and we can go straight to creating the replication tasks. Replication is basically mirroring of every snapshot from the SSD pool into the location chosen on the HDD pool. The replication will be activated on an hourly basis to match the snapshot task frequency. However, in this operation I will be extending the lifetime of the original snapshots to 6 months. This will retain a longer history of the data on the HDD pool, where we have much more space. We are almost done with the hot storage backup. The folders containing replicated snapshots can be accessed via a Samba share if needed. Unfortunately, this configuration will always reflect our working copy state, and we have only around 7 terabytes of fast storage. After a while I want to move the old data to some kind of historical archive, accessible if needed. However, removing an old project from the working copy would be reflected in the hot storage backup, leading to potential data loss after 6 months when the snapshots expire. That's why we want to create an additional place on our hot storage, which will be an archive. We can do this easily. First, we create a new dataset in the HDD pool. Let's call it Cold Archive. Cold because I do not want to modify existing data inside it in any way ever. Reminder that the hot in opposition to cold storage, can be used as a working copy if needed. Now we need to create local SSH credentials. We do it in the Credentials tab, and you can see that I've already created one called local. But let's look at the creation process. We make a connection to the server that we are currently working with, and we will use an admin account for that. We generate new SSH credential for the admin user and click Save. Now we can use this credential to create an rsync task. During creation, we use the SSH connection from the keychain that we created beforehand. Rsync is a very straightforward and well-known command line tool that synchronizes the source and the destination data. In this configuration, it will modify or add new files, but will not delete the existing ones. Because it is performed with admin credentials, you may encounter some permission issues if you ever want to modify the existing folder structure of your archive via some dangerous manual modification using Samba connection, for instance. Newly created folders with your user credentials may not be accessible to the admin account performing rsync, so you will have to correct the POSIX permissions afterward. Take that into consideration, and it is best never to modify your cold archive directly. Of course, we want to have snapshots of our archive, so we add periodic snapshot tasks to the configuration. We are almost ready now. In fact, if our cold archive were synchronized on another offsite machine, we would be done. But in this case, I wanted to have my historical data easily accessible on the local network for fast access. This allows me to restore any substantial project from the archive in minutes, hence we still need to back up our data offsite, and for this purpose I will be using Duplicati software. Duplicati is an open source program that can compress, encrypt and serialize your data and put it wherever you want it to be. It can use hard drive, a cloud service, an object storage or another NAS. There are a lot of options. The TrueNAS has its own application for Duplicati, which is essentially a Helm chart for Kubernetes running on TrueNAS. While TrueNAS apps are very useful, this time we'll use the standard desktop Duplicati application installed on a Windows virtual machine. It is not perfect from an administration point of view, but I will personally use a Windows virtual machine to run the Davinci Resolve project server and many other custom software that unfortunately needs Mac or Windows present. So basically you have several options here. Leverage the apps functionality of a TrueNAS, run it in a Docker container on a TrueNAS, or install it on a Linux or Windows virtual machine running on a TrueNAS. You can easily deploy many virtual machines on TrueNAS, and we've got plenty of resources for that. Fortunately, my machine lacks a TPM module for the Windows 11 installation, so I went for a bit longer road by installing Windows 10 and upgrading it using the Rufus program. When dealing with Windows on TrueNAS, remember to install virt.io drivers for Windows and switch the network device and local drives to virt.io drivers for better performance. They are much faster. Once Windows is set up, I installed Duplicati and mapped network locations with my archives. For the purpose of this video, I'm configuring a straightforward backup task targeting local main I/O storage, but after that I will create dozens of different backup tasks for various folders in my archive and connect it with my private offsite S3 storage provider. It's always better to create many smaller tasks, as Duplicati has some drawbacks. For instance, it won't recover from network disconnections if the entire backup hasn't been completed at least once. This becomes an issue if you are attempting to backup 20 terabytes of data at once over a 100 megabit internet connection. So it's just more efficient to use different backup schedules for different data segments. In reality, I've been using the system for a few weeks now, and the configuration works great. And of course, I've upgraded my working station connection to 10 gigabits. I hope this video will help you create your own backup solutions, but don't blame me if the construction and configuration process will take days for you. There are many topics here that I've only skimmed over, as proper credentials and permission configurations. And the new variations to the setup shown here can prove to be exhausting and lesson-filled journey. While navigating the intricacies of software and data, remember that if you ever want to go back to the photography and filmmaking content, subscribe to the channel.